Students, we are doing potential due to a point charge. We know the potential energy, that is equals to Q by R. R is the distance between these two charges, configuration of charge. R is the distance between them, this point P and this origin, suppose. So V is potential energy per unit charge. So this V is representative of source charge only. So potential at P due to Q is KQ by R. This is the formula that we are going to derive. And we are studying about conservative force here. Electric force is conservative force. When I am bringing this from infinity, this charge, there is no force on it when it is at infinity. No repulsion, because the distance was so much. Now I am reducing this distance. So at every point, this electric force is increasing as it is coming near this positive Q to this source charge placed at origin. And we know the formula. Coulomb's force between them is given by this formula. So as R is reduced, so this Fe will increase. So it means this conservative force, the variable force, first thing. Second thing is work done by this conservative force, by this electric force, depends only on final and initial positions, independent of the path, where you are bringing it over this path or here, or let it move round and round and then come here, doesn't matter. Work done is not going to have an impact. Next thing is that work done by, so E is the electrostatic force and external. So work done by external force will be stored in the form of potential energy when you will bring this charge at infinitesimally small speed with acceleration is equals to 0. Okay, so there is no acceleration. So no acceleration means you are applying exactly the same force in this direction, that is F external force, which is equal to Fe, so that there is no acceleration. Then only the work done by external force will be stored as potential energy. So that's the condition. Acceleration is 0. So acceleration 0 means F net force will be 0. So net force means the electric force is equal to external force. So both these forces are exactly equal. Okay. Now the next thing that we must know is that work done by as the displacement is in this direction, so work done by external force and displacement, they are in the same direction. So work done by external force will be positive, okay, and work done by electrostatic force will be negative. So your positive means your final answer, suppose it is 10, so final answer must be positive, it is 10 joule, and work done by electrostatic force will be exactly equals to minus 10 joule, because forces are equal, displacement is same, forces are equal and opposite, so that is why magnitude will be same, but work done by external force will be positive and this one will be negative. Now I want to derive this formula. So if I put Q is equals to 1 coulomb plus 1 coulomb, so then I simply have to prove that V is equals to U, and U is nothing but the work done, and that's equals to KQ by R. So condition is that I am putting Q is equals to plus 1 coulomb. Okay. So then the work done on 1 coulomb charge in bringing it from infinity to at this point, suppose this point, let it be this point, this is point P here. So to this point P will be, and this is the distance r, this is the distance r, so this r is this distance, so potential at P due to this source charge Q. So I'm bringing this plus 1 coulomb charge from infinity to this point. So whatever the work I will done will be the potential at this point P. Okay. Now we have some intermediate point, that is P dash over here, and this distance is at P dash, this distance is R dash. Okay. Now as we did in the case of capacitor, we will just find the small work done for small displacement delta R. So for small displacement, let it be delta R dash. There also we took it as delta Q dash, because the charge on the plates were Q. If you remember, we did the derivation of parallel plate capacitor, energy stored in parallel plate capacitor. So same is the case here, intermediate stage, and at intermediate stage I have reached here at this P dash. So what I am doing, I am bringing, so bring plus 1 coulomb test charge from infinity to P. So here I am bringing it here. So on this path I have this P dash also. Okay. Now at some intermediate point, P dash on the path electric force or electrostatic force on plus 1 coulomb is, what will be the force? So this diagram is given in your book also, figure 2.3. So this is the derivation I am writing over here. So at some intermediate point P dash on the path, electric force on 1 coulomb is given by, so that's the formula, F is equals to KQQ by R square. So electric force is equal to, well, I am writing the magnitude only, K capital Q, force between this charge and plus 1 coulomb charge over here. Okay, so K is equals to 1 upon 4 pi epsilon naught, that is Coulomb's constant. And what is another charge? This test charge Q is plus 1 coulomb divided by this distance here is R dash. So R dash square. So this is the magnitude. If I would like to write it in vector form, so put the arrow over here. So this is the magnitude. So multiply it with the direction as unit vector. So what is the direction? See, this is vector R telling the position of P. This is vector R dash from O to P dash. So from O to P dash, then we have vector R dash. Okay? So it means R dash cap will be the unit vector in the direction of r or direction of r dash. Now we have done the work, right, against this force, So work done by external force against electric force from r dash vector r dash to vector r dash plus r dash plus delta r dash. Okay. So that work is given by, so it will be small work done. So the work done will be delta here. So in moving from this point to this point. Now students, what is this r dash? R dash vector. You can see here that this origin, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 like this. And so we have 9 over here and 10. So these are the position, right? And what is delta r here? Final position minus initial position. So final is 9. You are moving from here to here. So 9 minus 10. What is it? Minus 1. So delta r is your negative here. Delta r is negative. Okay. So now delta r is negative. And what will be the work done by external force? Work done by external force will be positive because external force and your delta r both are in same direction. So they are in same direction. Theta is equals to 0. So the work done will definitely be positive. So work done by external force is definitely positive. I have written it over here. Work done by external force is here positive, but in this term means your final answer will be positive. Now work done by external force as will be exactly equals to, because F net force must be 0, then only this whole work done will be stored as potential energy. So this electrostatic force is and external force both are exactly equal. So that's equals to means minus F external. So magnitude is same but direction is the opposite. So F external force, what is the magnitude? The same magnitude, because acceleration is 0 here, students. Then only the whole work done will be stored as potential energy. So, and that's the case for conservative forces. Now this external work will be equals to force into displacement. Theta is 0 here. So K Q by R dash square. So magnitude of force into magnitude of displacement because theta is 0, so cos theta is. So what is the displacement here? Delta r. Now look at this. Q is, I know the value of Q, it is positive. This Q charge is also positive. This Q is, so we have placed, you can write here that consider this point, we have forgotten to return, consider plus Q at origin. This is also we need to write. So this Q is also plus, and square of any distance also plus. So it means this number is plus. But what about delta R? Delta R is negative. So I put the value of delta R negative here. This work done will be negative, but this work done cannot be negative. This is positive. So that is why I need to put here negative sign. Is this clear, students? Why have I put here negative sign? Negative sign appear. Why it appears? It appears because delta R is negative, because delta R dash is delta R dash, right? Because delta R dash is negative, less than 0. And you have understood here, delta means final minus initial. Final position is 9, initial is 10 suppose. So final minus 9 minus 10 is minus 1. So this is negative. And that is why I have to put here negative sign. In lot of books and lot of explanation that I have seen, they are writing here the work done by external agency, but using this force by force as Fe and telling that the angle between the Fe and delta R is 180 degree. That is completely wrong, because when you are writing the work for the external, work done by the external agency, so this will be external force into the displacement. So they are using here, they are writing here external work done by external agency, and then writing here electrostatic force and telling that the angle between the electrostatic force and the displacement is 180 degree. That is why there is negative sign. This is wrong. Okay, so you cannot take that. So in a lot of books it's wrong. Even in SLODA this concept is given wrong. So students, you need to even in a lot of videos on the YouTube this concept is given wrong. So that's the main concept. Why do we have negative sign here? Not because theta is 180, theta is 0, but delta R is negative here. So negative, negative. I know that this work is supposed to be positive. And positive in what sense? Like positive 10, positive 11, positive whatever it is, positive x. I mean, this is some definite value and with positive sign. So that is why I need here negative sign. So I hope you have understood it. So work done by electrostatic force is then it will be electrostatic force into displacement. It is a dot product of that, and it is also the dot product here. So that's we need to see, students. But the work done, I know that it is positive work. So this delta R dash is negative. So this is the negative figure I will get. So to make it positive, I have to put here negative sign. Now, so this is delta W, small work done, small displacement, and this will be positive. Now what will be the total work done? Total work done by this external force, we will get it by integrating both sides. So this side integrating, I get total external work done. And what about integrating this side? So what is the initial position to final position? So what is the initial position? Infinity. What is the final position? I have to reach here, this position, r distance from the origin, and that's k q by r dash square into dr dash, and that's equals to, now you people are comfortable with the integration, there's no problem with constant will come outside, so minus kq and infinity to r 1 by r dash square dr dash. So x raised to the power minus 2 dx means x raised to the power 1 upon x. So x raised to the power minus 2 dx means its integration will be x to the minus 2 plus 1 divided by minus 2 plus 1, that is minus 1. So x raised to the power minus 1 upon minus 1, that will be equals to minus 1 upon x, plus if this definite integral, then we have to write the units here. So if it is, suppose infinity to r means x, suppose, or r, whatever it is, so here I will have the units over here means infinity to r. So this is, so it will be minus kq minus 1 upon r dash from infinity to r, and this will comes out to be minus minus, it will be positive, and then putting the kq, putting the final value 1 upon, so minus minus will be positive, right? 1 upon r minus 1 upon infinity, and that will be equals to k q by r, because 1 by infinity is 0. And this external work done, this work done by the external force will be the potential at P. So this was the derivation of the potential due to a point charge. Now students, very important thing is the graph that we have, which is figure 2.4. So look at figure 2.4. I hope you people have your NCRT page number 55. This comes as 1 mark question in board exams. So what do we have? This is x-axis and y-axis. So this is your R, and this is your, here you have E or V. So now you have this charge Q at origin, and this is point P, which is at a distance R. At this point, what is the potential at this point? What is the electric field at this point? So they are sole representative of source charge only. So whether you keep here test charge or not, it doesn't matter. Potential is there, electric field is there. And when you bring the test charge to test whether there is electric field or not, definitely you will find that electric force will act on it, and it will move in such a direction. So electric force, conservative force, next point students that you can write here is that the conservative force means the electrostatic force will act in the direction of decreasing potential energy of source charge. So in which direction Fe? So these are very important basics. Force, this conservative force will always act in the direction of decreasing potential energy of the test charge. So if you put Q over here and both are positive, so it will move away. So in this direction, potential energy is decreasing. And we'll also do a derivation, next derivation, how electric field will behave. Okay, that's our next derivation. So now I was telling you that V and E are sole representative of source charge, and V is equals to K Q R into R. So that is E, sorry. Electric field, magnitude of electric field at this point P due to this. Okay, and this is what your V is. So E is equals to V by R, or V is equals to ER or ED or EL, anything. So this was your E and V is your KQ by R. See, here it is Q square. So this electric field is inversely proportional to Q square, and potential is inversely proportional to R. So E decreases at faster pace. As you move away, this distance increase. E becomes lesser, more lesser than the potential, because here we have R inversely proportional, here we have R square. So let us draw this diagram, how to draw it. See, at 1, it doesn't matter whether it is R square or R, because square of 1 is 1 and 1 is 1 here. So at this point, both will have, at R is equal to 1, both will have the same value. Now if this is greater than 1, when this is greater than 1, suppose 2. Okay, so which one will be greater? This is constant. So 2 square means 4. Okay, so this is 2. So square of 2 is 4, and this will remain only 2, and it is 4 times, means reduced as compared to this 2 times. So electric field will be lesser as compared to the, so here if we draw the graph, this is suppose electric field, and this will be the graph of potential. So if we have 0.5 here, so it will become 0.5, so it will become 0.25. So 0.5 multiplies 0.5 is 0.25. So here and here it will be 0.5 only. So that is why at this point, at 0.5, V will be greater. Sorry, E, this is E, and this is V. This one is E, so E will be greater, because here 0.25 means this value is lesser, so electric field is more. Okay, so this is greater, 0.5 is greater. So that is why this will be lesser than this. So E will be greater and V. But here at 2, so here at this point, this E will be greater than V. Okay, and here at 2, this is V dash. V dash will be greater than E dash. Let it be E dash. So student, this when you will draw graph, this will be the case, and it is only due to r square. So this is the graph of 1 by r square. So this graph can be anywhere, as for other relations also. So this is the graph of 1 by r, and this is the graph of, which is this is E, not V, this is E, and this one is of V. So for V, it is, this graph is 1 by r square. Okay. So electrostatic field is inversely proportional to r square, and V is inversely proportional to r. So V is inversely proportional to 1 by r. So this is our graph of r versus V. Or so this graph is actually for 1 by r and 1 by r square. Whenever you will be comparing, so you will find this graphs. Okay. Now if we do example 2.1, we have done it, but let us just do it very simple. So calculate the potential at point P due to the charge. So we have a point here, and this is due to the charge at origin. This is the source charge, which is 4 into 10 power minus 7 coulombs. So what is the potential at P here? So potential at P, which is this at distance 9 centimeters, so 0.09 meters. So V is equals to K, 9 to 10 power 9, KQ by R, and this will comes out to be 4 into 10 power 4 volts. So that is the potential at P. Now from infinity I am bringing a charge equals to 2 into, so that small q into test charge, minus 9 coulomb. This I'm bringing at P point from infinity. So how much is the work done? So the work done will be equals to, you can see we have written the formula here. That this is the formula that we have written, that V is equals to potential energy by Q, and this potential energy is nothing but the work done in bringing, so this from infinity to P. So potential energy will be stored, that is what work done by the conservative force is stored as potential energy. So work done by conservative force, so you can add this 6th point over here, that work done by external force, sorry, not the conservative force, work done by the external force against Fe. We have used it in this derivation. Against Fe is stored as potential energy of Q. So that's the 6th point about the conservative force. Okay students, and that is why we need to integrate it. We need to use the formula for the work done, total work done by the conservative force, and it was variable force. So work done by the external force. So electric force was varying, so in the same way external force also was varying, because both were equal. So that is why it is variable force. So we have used this formula, because F electric was equals to F external, then only the acceleration will be 0, and whole work done is stored in the form of potential energy. So students, remember these regulations for the conservative force. They are same for the spring force and gravitational force that we did in 11th class. Okay, so now we need to tell the work done. Work done will be, we have just seen that V is equals to U by Q, and that is W by Q. So work done is equals to V by Q. Remember one important thing here, that this V is, when we are doing the work, this U is when I'm bringing this K from infinity to point P. So at infinity, I'm assuming the potential energy to be 0, and potential is also 0. So I'm assuming this V, when, see, delta V is equals to V final minus V initial. So that is V at point P minus V at infinity. V at point P is V, and V at infinity was 0. So that is why change in potential, the potential difference is the same, the potential at P, because at infinity it was 0, right? So students, this formula is for the case when the charge is bringing the charge from infinity. If I'm not bringing the charge from infinity, but from these 2 points, so I have potential here at Q and I have potential here at P. So then this will be delta V by Q, and delta V will be V final Vp minus initial Vq. So remember this, that this formula is actually work done by delta Q. But in the special case, when this Vq is infinity, then, and this Vp is the potential at P, then it will be equals to delta V is equals to V. Okay? So as the charge bringing from infinity, so change in potential from here to here it was 0, and here the potential we know it is V. So that is why we can use delta V by Q. So always write this delta V by Q, and that is equals to V by Q. Okay? So that is the case when we are bringing Q from infinity. Now this will be equals to V 4 into 10 to power. So what is so Q into V or V into Q, it's the same thing. So V is 4 into 10 to power 4 into 2 into 10 to power minus 9 coulombs. So the work done depends on the potential. Okay? So, and you know potential is equals to KQ by R. So potential increases. As this R decreases, potential increases. So the potential was 0 here, and here it is 10 into 4 into 10 to power 10 multiply 4 means 40,000 volt, and if you will bring more near, it will be 50,000 volt. Okay? So it is increasing, and more is the work you need to do. Yes. So it depends on the potential, right? So more will be the repulsion, so more work you are doing. So this comes out to be, so how much work? 8 into 10 to power minus 5 joules. So that is the work, students. So now potential due to electric dipole. So we have and this is especially at point dipole. So we have in the exam the question comes like potential at a point along the axial line of an electric dipole. So this question actually comes in exam, which is a special case of the derivation given in your book, but we don't do this question as special case, we do it separately. We have to find the, so this is minus Q and this is plus Q, and this is the axial line, and this is the point, suppose this is the midpoint, and this is, let it be point P. So where we are supposed to find the potential, or you can take it as O also. So what's the benefit of if I am taking it as O? So here you have to find the potential. So the advantage is that I can take it as R, and this I know that this distance is A and this distance is R. Now potential at O due to dipole is V equals to, so obviously we have two charges, so potential due to minus Q and potential due to Q, and both potential is a scalar quantity, so we can simply add the potential due to plus Q and potential due to minus Q, students. So it's so simple. Okay, now let us find it. That will be given by K Q, that is plus Q, divided by R. So what is R here? In case of plus Q, what is the distance from O to plus Q? This distance is okay, students, see, one thing we need to understand it, that the distance is, in case of dipole, is always taken from the midpoint. Okay, so this distance R is from the midpoint. Always take the distance from the midpoint to the point where we need to find the potential. So this distance will be R minus A. So that's R minus A plus, what is V minus Q? So K into minus Q divided by, always take the, I told you that in case of F, K, Q by R square. So take the, don't take the sign consideration here. Only find the magnitude of the force, and you can tell whether they will attract or repel. You can tell the direction. Similarly here also, K, Q by R square. Don't consider the sign at both the places, but for U, that is K, Q by R, yes, we will consider the sign. For V also, we will consider the sign. And these two are scalar quantity, these two are vector quantities. So students, this you always need to keep in mind. So take, yes, definitely we are going to take the sign of the charges. And what is the distance O to minus Q? This distance is, this R, this is again A. So this will be R plus A. So R plus A. And this will comes out to be, so what is common here? KQ. KQ is common. So 1 upon R minus A minus 1 upon R plus A. That will be equals to KQ into R square minus A square and R plus A minus R minus A. And this will comes out to be KQ into R square minus A square, and this is so R plus A minus R plus A. So R will cancel out, and this will comes out to be K into 2AQ upon R square minus A square. And what is 2AQ? That is here P. So this will be Kp upon R square minus A square, and where K is equals to 1 upon 4 pi epsilon. So that's the potential at O. So students, we need to find the potential this way. So I hope you have understood these concepts, and do the example 2.3 also today based on this concept. So you'll be able to do it. Understand one thing that I have discussed here. All these points, that electrostatic will act in the direction of decreasing potential energy, and external force will act against Fe to increase the potential energy. So who is going to increase the potential energy? Force external act against Fe, potential energy will increase. Fe act such that potential energy will decrease. So external force acting against this potential energy increase or decrease. So now you have plus charge, minus charge. So you can do this example 3, keeping in mind this concept. Now we'll do one more small derivation today, quite important. Students, keep some patience. So this is a kind of discussion. I'm not in hurry I'm taking time, letting time to absorb you all these concepts. Very important concepts, students. Relation between field, of course electrostatic field and electric potential. So what is the relation between them? So we have here two surfaces, equipotential surfaces, and this is the direction of electric field. So obviously you can always assume that electric field lines, they are coming from positive and going towards negative, right? So this is V potential, and I have a point here A on this surface, and there is a point. So this is point P. So this is equipotential surface A, and this is equipotential surface B. So of course this is a plane as it is shown in your figure. So this is a plane, this, and this is also a plane, equipotential planes. These are not line but the planes, and the potential here is V plus delta V. So we have these two closely spaced equipotential surfaces. So distance is also between them is delta L, and P is the point on surface B. Now imagine one positive Coulomb charge, unit positive, is moved along the distance delta L from surface B to A. So 1 Coulomb is moved from B to A against electric field. So as I told you that you are moving plus 1 Coulomb charge from P to the surface A. So don't take this point as A, but this whole is equipotential surface A. So from this point P, obviously this is perpendicularly I am moving against the electric field. So electric field is in this direction, so positive charge over here negative, and I am bringing this positive in this direction. So obviously it is going to be repelled by the electric field. So that is why this is moved from this to against this. Who is moving this charge? Who is moving it? It is moved by external force. Okay, this is moved by external force. So what is the work done by the external force in this process? I told you again, students, that in the conservative force, this is the external force you are applying. This is exactly equal to F electric, means the electric force, electrostatic force is equal to, they are exactly equal, because acceleration is 0 here, and you know Newton's third law, F net is equals to ma. So if F net is 0, if A is 0, then F net will also be 0. So it means both these forces are equal. So that's for the conservative forces. So F is the conservative force, and that. So F external, we did in the first derivation also for the potential, the same force. So electrostatic force we calculated, and we take it as a external force. Okay. So here this work done will be positive, because that is the direction of displacement delta L, and that's the direction of force external acting on +1 coulomb charge. Okay. So bringing +1 coulomb external force is acting. So the work done is equals to F force into displacement, and you know that the angle is 0 degree, so cos 0 is 1, and that's equals to, what is the force? I told you that this external force is exactly equal to electric force. What is electric force? Q into E. So QE delta L. Now what is E into delta L? We discussed this formula. E into D. We have written it here, that E into D, E into L, so that will be equal to this potential difference, right? Everywhere we have written potential, because we are talking about from infinity to that point. So that is equals to Q so this is the work done by the external force, that is equals to QE delta L. Now what is Q here? Q is +1 coulomb, and I told you what is this E delta L, that is change in potential, right? Okay, so that's the work done by external force. So +1 coulomb, so it means work done by the external force is equals to change in the potential, and you know that the work done by external force is equals to change in potential energy, change in potential energy, and if you divide them with Q, you get V. But this is the case when we are from infinity, so this is actually delta V. So this is delta V here. Same thing. Now this E, let us write this thing again. So magnitude of E into delta L is equals to change in potential and that's equals to V final minus V initial, and that's equals to, what is V final? V final is V. What is V initial? V minus delta V. And this equals to E delta L is equals to, so V cancels out and it is equals to minus delta V, and E is equals to minus delta V by delta L. So that is the magnitude of E. Now there's one more thing to it. We know that for this positive charge, if I'm bringing it against the direction of force, so potential energy will be more, and potential is more. We did it in the last example also, that potential will increase because so here the potential is increasing, so it means this delta V is actually negative quantity. So this E is equals to, this delta V is negative. So this is equals to minus I can write this delta V as minus delta V. See, this modulus means this is positive, and then I put negative here. So this is tell me that definitely this is negative, and I know that this is negative. So that is why delta V is negative. Delta V is negative. So how to make sure that something will be negative? So that is the way. First make it positive, so it will always be positive, and now put the negative sign. So this number will always be a negative number. So that's why I have put here that delta V is equals to minus delta V, because this tells that this is a negative number. So this is the only way to show that this is a negative number. Now this negative will be positive. So it means this magnitude of this electric field, it will be positive. Okay. So sometimes from here we write E equals to minus dV by dr also. But actually, that's the main formula. E is equals to, and don't forget this modular sign will remain there. So that's the magnitude of E. Now we have two important conclusions to draw here. What are those important conclusions? So the conclusion, the first one is that electric field is in the direction of electric field in which potential decreases steepest. So electric field is in the direction where direction of potential decreases steepest. So here the potential was increasing, and here perpendicular moving, the potential is decreasing. So it is decreasing at the highest pace. And the second thing is that the magnitude of E, electric field, is given by change in the magnitude of potential per unit displacement. So they are written in your book also. So change in potential per unit displacement, and this displacement is normal to the equipotential surface at that point. So this displacement is perpendicular to the equipotential surface at that point. So that's the electric field per unit displacement. So another way of describing the electric field. So thank you, students.